Welcome to the second session of Electrochemistry unit, 13th unit. In this session, you can learn how to write cell notations correctly, types of cells, qualitative and quantitative aspects of electrolysis. First, let us see whether you can remember the last slide of our previous session. There you learnt how to write reduction half reactions at cathode, that is copper electrode, and oxidation half reaction at anode, that is zinc electrode. So, these are the cathode reaction and anode reaction of Daniell cell. These are the cathode reaction and anode reaction of Daniell cell. Two portions of the cell are called half cells. Copper electrode is the reduction half cell and zinc electrode is the oxidation half cell. Now, you can write the cell reaction of Daniell cell. So, here you can see it is written copper 2 plus aqueous plus zinc solid convert into zinc 2 plus aqueous copper solid. Next, let us see what will happen if an external opposite potential is applied to galvanic cell and increased slowly. Reaction will continue to take place till the opposing voltage reaches 1.1 volt. Then the reaction will stop at 1.1 volt and no current will flow through the cell. As a result of further increase in the external potential, reverse reaction will occur. So, you can see the reverse reaction here, copper solid with zinc 2 plus aqueous, you will get copper 2 plus aqueous plus zinc solid. Now, it functions as an electrolytic cell. Then let us see what are these cell potential and electromotive force. The potential difference between the two electrodes of a galvanic cell is called the cell potential. It is measured in volts. When there is no current through the cell, potential difference between the two electrodes is called electromotive force. If there is an electrochemical cell where two electrodes are in two different electrolyte solutions, there is an additional potential difference arise across the boundary, and this is called liquid junction potential. So, salt bridge can be used to minimize the contribution of liquid junction potential. Now, let us see how to write the cell notation. Cell notation represents the electrochemical cell. These are the important points you have to consider when you are writing cell notation. First one, anode is written on the left hand side and cathode is written on the right hand side. Phase boundary is represented by a vertical line. Dotted vertical line represents the liquid junction potential, liquid junction potential. Double vertical bars represents the salt bridge. Physical states of all species and conditions should be indicated if known. Then look at these examples. There you can see vertical bar is separating platinum and gaseous hydrogen. So, two different phases. Then again there is a another vertical bar in between H2 gas and 2H plus aqueous, again 2 phases. Then double vertical bar represents salt bridge. Then on the right hand side, magnesium 2 plus vertical bar, magnesium solid, that is cathode. So, on the left hand side you can see the anode, and on the right hand side you can see the cathode. Cathode is reducing. At the anode you can see the oxidation reaction takes place. Then let us see how to calculate cell potential. Here we are using this equation, E naught cell equals E naught right minus E naught left. That means EMF of cell is given by the potential of the half cell on right hand side minus the potential of the half cell on left hand side. Otherwise, you can give that equation E as E naught cell equals E naught cathode minus E naught anode. So, for Daniell cell, you can calculate E cell using the values 0.34 volt for copper electrode. For zinc electrode, it is minus 0.76 volt. So, you will get 1.1 volt as the cell potential. Here you can see different versions of Daniell cell. In the first version, there's a salt bridge. They are using salt bridge. You can minimize liquid junction potential. But in the second diagram, there is no salt bridge. Zinc sulfate solution is included or contained in a porous pot. So, there is a liquid junction potential because of the liquid junction between the two different electrolytes. Next, factors affecting the electrode potential. There are 4 factors: the temperature, concentration of the electrolyte, pressure of the gas, type of the electrolyte. First one, temperature; second one, concentration of the electrolyte; third one, if there is a gas, then pressure of the gas; fourth one, type of the electrolyte. Okay, then let us see what are the different types of galvanic cells. There are 2 different types, primary cells and secondary cells. See what is the difference between these 2 cells, 2 types of cells. For primary cells, the cell reaction cannot be reversed by providing electrical energy, and they are not rechargeable. Primary cells are not rechargeable, but secondary cells, they can be recharged because cell reaction can be reversed. Then we can give 2 examples for primary cells, normal Leclanche cell and Daniell cell. Then here you can see secondary cell. They are rechargeable batteries. Reaction can be readily reversed. Similarly to primary cells, except redox reaction can be reversed. When recharging, electrodes undergo the opposite process than discharging. So, cathode is oxidized and produce electrons. Electrons absorbed by anode. So, this is lead accumulator secondary cell. It can be recharged by reversing electrochemical reaction, that is also known as car battery. Here we have compared 3 cells, normal Lagrange cell, Daniell cell and lead accumulator. So, you can see the differences. When we consider the electrolyte, for normal Lagrange cell, that is ammonium chloride and zinc chloride, Daniell cell zinc sulphate, copper sulphate, lead accumulator, it is dill H2SO4, dill sulfuric acid, and positive pole carbon and manganese oxide. For Daniell cell, it is copper, lead accumulator, lead oxide PbO2. Minus pole or negative pole, normal Lagrange cell, negative pole of normal Lagrange cell is zinc, Daniell cell zinc again, lead accumulator lead. Then you can see the cathode reaction relevant to normal Lagrange cell. There ammonium ions react with manganese dioxide, forming Mn2O3, manganese oxide, H2O and ammonia. In Daniell cell, cathode reaction, copper 2 plus gains 2 electrons, convert into copper solid. Lead accumulator, during discharge, lead oxide PbO2 reacts with H plus sulphate and 2 electrons there, forming lead sulphate and water. Anode reaction of normal Lagrange cell, there you can see zinc is converted into zinc 2 plus and 2 electrons. So, it is oxidizing there, zinc is oxidizing. In Daniell cell also you can see zinc is oxidizing, zinc convert into zinc 2 plus. In lead accumulator, anode reaction, lead reacts with sulphate ions, forming lead sulphate and 2 electrons. So, then you can write cell reaction for all 3 cells. Then let us see what is this electrolysis. You know, electrical energy can be used to carry out non-spontaneous reactions. This is known as electrolysis. During electrolysis, the electrode connected to positive terminal of the external source of electricity is anode, and the electrode connected to negative terminal of the external source is cathode. Now, let us see what will happen when electrolysis of water is going on. So, you can see the cell reaction relevant to this electrolysis of water. They are H2O liquid will convert into H2 gas and oxygen gas. So, gives free energy, they are given 474.4 kilojoule per mole. You can see it is a positive value. That means that reaction is non-spontaneous. So, in pure water, you know, H plus concentration equals OH minus concentration, that is 1 into 10 to the power minus 7 mole per cubic decimeter. Therefore, dilute sulfuric acid is added to water. Then solution has more ionic species, so that conducting electricity will be more feasible. So, there you can see the anode reaction and cathode reaction relevant to electrolysis of water. At anode, liquid water H2O converts into oxygen plus H plus and electrons. At cathode, H plus reacts with electrons to form hydrogen gas. So, overall reaction H2O gives H2 gas and O2 gas. This is the apparatus relevant to electrolysis of water. There you can see the anode. At the anode, oxygen gas is evolving. At the cathode, hydrogen gas is evolving. Then next, electrolysis of copper sulfate using copper electrodes. This is used commercially to purify copper. Positive electrode is impure copper and negative electrode is pure copper. When the system is connected to an electrical source, impure copper rod will be dissolved and more copper will be deposited on pure copper rod. Now, here in this diagram you can see what is happening actually. So, you can see copper cube Cu2 plus ions in the solution attracts towards a negative cathode electrode and sulfate ions and OH minus ions attracts towards positive anode electrode. So, and at the anode you can see oxidation will occur, copper solid will convert into cupric Cu2 plus and copper rod will be dissolved, copper anode is dissolved in there, and at the cathode Cu2 plus cupric ions gain electrons and they will deposit on the copper metal, copper rod. So, positive ions are attracted towards the negative electrode, gain electrons. So, they are reduced. They become Cu2 plus ions become copper, reduced to copper. Now, let us see what will happen if we proceed electrolysis of copper sulfate using inert electrodes. When inert electrodes are used, oxygen, here O2, oxygen is released at the anode and deposition of copper is occurred at cathode. So, you can see the anode reaction and cathode reaction. At the anode, H2O converts into oxygen gas and giving H plus and electrons. At the cathode, Cu2 plus convert into Cu, copper solid. Overall reaction, you will get 2H2O liquid plus 2Cu2 plus, that is aqueous, giving copper solid, oxygen gas and 4H plus. Here you have to indicate physical states. Let us see what will happen when aqueous sodium chloride solution is electrolyzed using inert electrodes. There are three possible reactions at cathode. First one, 2H plus can gain 2 electrons and convert into H2. Second, 2H2O gain 2 electrons forming hydrogen gas and OH minus. Third reaction, sodium plus reacts with electron to form sodium solid. So, they are the E cell values, electrode potential values are also given. When standard reduction potentials are considered, most probable reduction is first one. Here it is given as second, that is not second, it must be first one. However, this reaction requires standard conditions and also H plus concentration in water is too low. Therefore, it is not possible under ordinary laboratory conditions. The third reaction cannot happen due to a large negative potential. Therefore, most possible reduction reaction that can happen at cathode is actually second. Then when we consider the oxidation reactions at anode, there are two possible reactions. Cl minus can be converted into Cl2 and releasing 2 electrons, and H2O can be converted into oxygen releasing H plus and electrons. So, when standard reduction potentials are considered, first reaction is more feasible. Therefore, chlorine will be evolved. So, you can see the electrolysis of liquid sodium chloride using inert electrodes. Then at the anode, Cl minus will convert into chlorine gas, Cl2 gas, and at the cathode you will get solid sodium, that means sodium plus, liquid sodium plus reacts with electrons to form sodium solid. So, overall reaction relevant to this electrolysis is Cl minus reacts with sodium plus forming chlorine gas and sodium, solid sodium. So, industrially sodium metal is extracted by this method. Industrial setup is known as Downs cell. Now, up to now we have considered qualitative aspects of electrolysis. Now, we can consider quantitative aspects of electrolysis. Michael Faraday was the first scientist who described the qualitative aspects of electrolysis. First law says the amount of chemical reaction is proportional to the quantity of electricity passed through the electrolyte. So, here it is given in an equation M is the amount of substance that is proportional to the quantity of electricity Q. So, you can get Q using I and T. Q equals IT, I is current, T is time. So, Z here, Z is the electrochemical equivalent. So, you can get M equals ZIT. Second law says the amount of different substances liberated by the same quantity of electricity passing through the electrolyte is proportional to the chemical equivalent of the substance, chemical equivalent, that is E. So, the relationship between Z and E is given by this reaction. Z equals E upon 96,485 coulomb, that is Faraday constant. Then you know M equals ZIT, so you can get, you can substitute that E upon 96,485 to Z, and you can write the equation as M equals E over EIT over 96,485 coulomb. Now we have come to the end of this unit. So you can go through these lessons over and over, then you will be able to write a correct answer for the questions based on electrochemistry. Thank you.